We are going to continue doing buffer problems. These next few problems that you're going to see are prime examples of how you're going to see them on the AP exam. So one problem, multiple letters. Each one starts out easy and it gets a little more and more difficult as you go through the problem. Congratulations to the Lees on the nuptials. I'm very happy I got to take a picture of your panda. It was quite an experience. That was great. That's a story for another time. So one thing I want you out of your head that we're working unit by unit. You're responsible for this unit for unit 10, 11, and 12 because this problem right here encompasses knowledge all the way from unit 10 through to what we know now. And it puts it all together and smushes it in one type of problem. Nothing you haven't done before, nothing you can't do, but sometimes it confuses people's heads. So let's start with this one. First off, what is the pH of a 2-molar solution of acetic acid? So looking at this 2-molar solution of acetic acid, classify this as a what type of problem? Weak acid. So how do I find the pH of a weak acid? Rice table. One thing that's a good trick for the AP, if I want to use HAC for acetic acid for time purposes, as long as at the top of the problem somewhere, you go ahead and indicate that's what you're doing, you're good to go. And make sure you do it on every problem you do. Know that the questions are graded independently. So say you want to do it on problem 1 and then again on problem 7. Grader for problem 1 only sees 1. Grader for problem 7 only sees 7. So you need to do any type of shortcut you do like that, please do it on every problem. So we're going to start a rice table. Write small on this paper, guys, because you're going to run out of room. All right, so we have acetic acid, and we're going to add it to water because it's weak. And we get AC minus plus water. We know water doesn't go in the rice table. What's our original concentration of the acid? 2.0 molar, and then 0 for the acetate, minus X plus X. What did I do wrong here? It's like we can't have 2 that, and we're not making water. Boy, it's a long day. And plus X there. So we can still trump this. Just indicate that. What do you need to indicate? That X is negligible. And so we end up getting X squared over 2 is equal to our Ka of 1.8 times 10 to the negative 5th. Solve for X, please. I've been really lax on showing work here, but one thing that's not negotiable is indicating that X is that H3O plus concentration. And you can check my numbers, make sure the other period did it right. They got 0.0060 here, and that's moles per liter. And the problem's asking for pH, so pH is equal to negative log of that. And when you take the negative log of 0.0060, you should get 2.22. So nothing you haven't seen there, right? But again, not Unit 12. I taught you that in Unit 11. Okay, so it's total cumulative knowledge. You are responsible for that. Okay, let's go on to Part B. Part B says, a buffer solution is prepared by adding 0.1 liter lightning bolt of, I'm just kidding, 0.1 liter of 2 molar acetic acid solution to 0.1 liter of 1 molar sodium hydroxide. We're not starting with a buffer. We're preparing a buffer by doing what? What type of problem are we creating here? What are we mixing? Acetic acid and sodium hydroxide. Yes, so it's an invader problem. So we have to do a Stoich table. We're adding the sodium hydroxide to acetic acid. And what are we making? Water and AC minus. Okay, there's our beginning of our Stoich table. So first thing we need to do is figure out the moles of each thing. The sodium hydroxide, it's 0.1 liter and 1 molar. So moles times liters gives us 0.1 to give us moles. HAC's moles is 2 molar times 0.1, so this is 0.2, 0, and we don't care. Again, looking at moles, which one's going to run out? The sodium hydroxide, so we're going to lose that many and gain that. Here's what they meant by making a buffer solution. Didn't we just create a buffer? Right there. That's the buffer we were making. Okay, so in order to find, what do they want from us? They want the hydrogen ion concentration. So let's go ahead and use the Henderson-Hasselbalch to find the pH, and then we can easily find the H+ concentration. But you're going to see something here. Due to the fact that these are the same moles, what else is the same? We divide by the same number of liters, so the molarity is the same. Remember effective buffers we talked about? What happens in Henderson-Hasselbalch when the molarities of the conjugate, that cancels. So for pH is equal to pKa plus the log of the ion over the acid. When these are the same, the log of 1 is 0. So all we need to do in this problem, because these are the same, is pH is equal to pKa. Okay, but let me show you. Because we're looking for the H, the negative log of the K is equal to the pH. So, and you're going to, I'm just going to show you the long way why we are doing way more work than we need to. That gives us a pH of 4.74, but we need the H+ concentration. What's 10 to the negative 4.74? We already had it. We didn't need to do that. It's 1.8 times 10 to the negative 5th moles per liter, and that was the answer to that part. All right. At minimum, the question was, do we need to show work for that? At minimum, I want you to state that, and then say due to this, that is, the H+ is this. What I crossed out here was in Henderson-Hasselbalch. So are you familiar with that? If not, you need to watch the video. Did you watch Friday's video? Yeah, you're going to be totally lost today, and there's nothing I can do about it. So you're going to have to go back, watch the video, because I can't reteach this part. We don't have time. Watch that video, and then watch this video again, and just hang on for dear life right now. Okay, that's the answer to B. Part C. Part C, suppose that 0.1 liter of 0.5 molar hydrochloric acid is added to 0.04 liter of the buffer prepared in A. Oh, what are we doing here? We're adding H+, so we're invading, but what are we invading? The buffer from above. So we're invading, I'll just draw the little picture. We're invading HAC and AC minus. Which one of those two things is the H+ going to react with? AC minus. So our invasion equation for the Stoich table, invasion equation. That's kind of awesome. It's catchy. The invasion equation. I'm going to use that. That is amazing. All right, HAC. So we're going to start the Stoich table. And looking at this, it says 0.1 liter of 0.5 molar hydrochloric acid. So how many moles in our Stoich table? 0.05. AC minus. Well, let's look up. We had a concentration, correct, of both of these are 0.1. And it says it's it's not 0.1. Watch out. We had a concentration of 0.1 from the buffer, but we only used 0.04 liters of it. So how much did we actually use? How many moles? 0.1 times 0.04 is, no, it's I'm confused. Hold on. Oh, that's number of moles. There's my problem. I knew there was a problem. Right here, this is moles. So we really needed the concentration here of these things, so we're going to have to back up. Forgive me, people at home. So going back to B, we mixed 0.1 liter with 0.1 liter, making this divided by 0.2 here. So the concentration of each of these is 0.5. All right, so now that's the concentration. This is the concentration of 0.5 times the liters of 0.04, making this 0.02. And we have 0.02 of this as well. They were equimolar in the solution. So how much are we going to lose? 0.02 minus 0.02 plus 0.02 is 0. This is 0.04, but I really don't care because what's the situation here? H winds, strong winds. So that's how many moles we have of our H+. We take our moles, we have to convert to molarity. What is our total volume? We had a 0.1 liter plus a 0.04, so that's a 0.14 liter. To give me an H+ concentration of 0.214. Moles per liter. And the problem was asking for the hydrogen ion concentration for that, correct? Yes, we did not need to find pH. So there you go. That's a lot, isn't it? I'm going to pause the video and answer any questions. All right, let's move on to the next page. Number 7A. I'm going to write down here because I really don't need this space and I don't feel like stretching. Well, I guess I can stretch. 7A says, a 4-gram sample of sodium hydroxide is dissolved in enough water, yikes, that's tall, to make a 0.5 liter solution. Calculate the pH of the solution. So what do I need to do? Find the moles of what? Correct. Moles of NaOH. So if I've got 4 grams divided by 40 grams per mole, that's the molar mass of NaOH. That gives me, where is my thing, my cheat sheet, so I can get my numbers right without having to do the math. I know, I'm looking beyond just this. I'm thinking ahead. Hold on. Okay. So this gives us a 0.1 mole, but that's of OH minus. But what do I need to find the POH, to find the pH? So what do I do to this? Divide by 0.5. So I get an OH concentration of 0.20 moles per liter. Take the negative log of that. I get a POH. I need 2 decimal places. They got 0.70. Therefore, pH is 14 minus that. 13.3. Does that match up? Okay. All right. So that's our pH of the strong base. Suppose that 4 grams of sodium hydroxide is dissolved in 1 liter solution that is 0.5 molar NH3 and 0.5 molar NH4. What kind of solution is that I underlined? Buffer. What are we doing to the buffer? We're invading it, right? So let's write our invasion equation and see what we get. OH, what part of the buffer is it going to react with? NH4 plus, and it's going to make NH3 plus H2O. Now we need moles for our Stoich table, and here's where the fun begins. We're putting 4 grams into 1 liter. So I need to figure out how many moles I'm putting in that 1 liter. How many moles is 4 grams? There we go. 4 grams is 0.1 mole. So I'm putting that into a whole liter, okay? And I'm dissolving it into a liter of 0.5 molar NH3. So how many moles of NH3 do I have? 0.5. And 0.5 molar, 1 liter of it, of NH4 plus. So I have 0.5 of that as well. How much am I going to lose? Minus 0.1, minus 0.1, plus 0.1. So that gives me nada, 0.4, 0.6. Those are moles. Now, because I'm doing Henderson-Hasselbalch, it would be legal for me to not convert those to molarity and just put moles into Henderson-Hasselbalch. Can anyone tell me why? Because it's the ratio. We end up dividing both these numbers by the same volume and putting them in, getting the exact same ratio. I'm fearful of encouraging that because that is the only scenario you can do that in. You can't do that when strong winds. You can't do that when you only have the ion. You can't do that when you only have the acid, because those go into a Rice table, which has to be molarity. So I'm a little worried, but we're going to do that, and we're just going to plug into Henderson-Hasselbalch. What are we looking for? We're looking for hydroxide ion concentration. So let's look at what we have. We have a base and its conjugate acid. So what version of Henderson-Hasselbalch do we have to use? POH is equal to the negative log of the Kb of 1.8 times 10 to the negative fifth plus the log. What goes on top? Which number? Which number? 0.4. The ion concentration, in this case moles is okay, over the acid moles, or base. Ion over acid or ion over base. So what'd y'all get for POH? They got, keep losing my spot, 4.57. Okay, and then we have 10 to the negative 4.57 will be equal to 2.7 times 10 to the negative fifth moles per liter. I'm doing that to get the OH concentration. 9 times out of 10 folks, they're just going to ask you for the pH or the POH. They rarely, it's in the older problems, they're more apt to ask you for that concentration. But, all right, again, I'm pausing the video to answer questions. Okay, 2 more problems. Oh no, we've got 8 to do. Yeah, we have 3 more problems. Yowza, let's hustle. A buffer contains 0.4 moles of formic acid and 0.6 moles of sodium formate in 1 liter solution. So those moles are really what? Molarities. So that's good news. Calculate the pH of the solution. What are we finding the pH of? What type? Is it an invader? No, what is it? Just buffer. So Henderson-Hasselbalch, pH is equal to the negative log of the Ka plus the log, what's our ion concentration? Yes, 0.6, I lied. Yep, over 0.4. And so when we solve, we get a pH of the 2 decimal places and 2 sig figs, 3.92. Done. If 100 mils of this buffer solution is diluted to a volume of 1 liter with pure water, does the pH change? Oh, it doesn't say ask. It tells you. The pH does not change. Discuss why. Well, you're diluting what? Yep, you're diluting both the acid and the conjugate base at the same time. Okay, so you're not affecting the overall pH. And how you can see that mathematically is that log of the ion over the acid. You're diluting these equally, so the ratio does not change in Henderson-Hasselbalch. Now, any other solution you diluted, it's going to change the pH because there's usually only one thing contributing to the pH, like a weak acid. Weak acid, put water in it, it's going to get higher in pH. Okay? Hydrolysis, put water in the salt, pH is going to change depending upon if it's a basic or acidic salt, whatever direction. Okay? Okay, keep going. A 5 ml sample of a 1 molar HCl is added to 100 mils of the original buffer solution. Calculate the H3O plus of the resulting. So again, what are we doing? We're invading a buffer, and what part of the original buffer is it going to react with? the formate, right? Don't worry about it. If you took the first H off, it doesn't matter. If you did COOH negative, that's okay. And that's going to make our formic acid. So we have a stoich table here. We need moles. So H plus is 5 mils, which is 0.005 liters times 1 molar, 0.005. We're taking 100 mils of the original buffer. And what was the concentration of the formate? 0.6. So 0.6 times 0.1 from here is 0.06. And then 0.04 from the original buffer times that same 100 or 0.1 is, 0.4 times 0.1 is 0.04. So how much are we going to lose? 0.005, 0.005, gain 0.005. So we end up having none of the strong stuff left, getting 0.0055 here, and 0.005, not 0.005, 0.055, 0.055, and 0.045 moles. And again, because we can go ahead and plug into Henderson-Hasselbalch because we have a buffer here, you don't need to convert those to molarity. We'll just plug them straight in. pH is equal to the negative log of 1.8 times 10 to the negative fourth plus the log of 0.055 over 0.045. They got a pH of 3.83. I hope that's right. And then 10 to the negative 3.83 because the question's asking for H plus concentration. They got 1.5 times 10 to the negative fourth. Can someone verify that? Okay, good. Okay, part D. An 800 ml sample of 2 molar formic acid. So we've got formic acid is mixed with a 200 ml sample of 4.8 molar sodium hydroxide. What kind of problem is that? Invader. So all we're doing is adding OH minus to the formic acid. And we're doing a stoich table. And when we do our stoich table, we find out that we get COOH minus. And again, it doesn't matter what H take off. The form is unimportant. All right. So moles of OH. To get moles of OH, I take 4.8 and multiply by 0.2. So that comes out to be 0.96. And then for the formic acid, I have 2 times 0.8, comes out to be 1.6. And then I'm not adding to a buffer, so I don't have any of that yet. I'm going to lose how much? Lose 0.96. Oh, goodness. Guess what we made? We made a buffer. And we have 0.64 here and 0.96 here. Okay, so what are we going to use since we made a buffer? Henderson-Hasselbalch, the pH version, since it's an acid conjugate base situation, negative log of 1.8 times 10 to the negative fourth plus the log, what's the concentration of the ion? 0.96. It's not really concentration, but we're allowed to use it because it's really moles. Don't forget that. This is just an exception with this equation. Over 0.64. It sure saves us some time, though. pH came out to be 3.92. And then the 10 to the negative 3.92, because again, we need the H plus concentration, is 1.2 times 10 to the negative fourth moles per liter. pausing for questions. All right, moving on. Probably going to make this a bit smaller so y'all can read it on your papers better, but starting with A, it says, from the systems above, identify the conjugate pair that best describes a buffer with a pH of 7.2. I don't know if you recall me talking about effective buffers being buffers that can take hits from both sides of acids and bases equally. So if I want that, what would I have in the buffer? Equal amounts of what? Acid and conjugate base. If that's the case, an effective buffer, Henderson-Hasselbalch, would look like what? pH is equal to pKa, and that's it, because that log thing would cancel out, right? Or pOH is equal to pKb. So keeping that in mind, if I want to make an effective buffer with a pH of 7.2, which one is going to be the best one up there? A, B, or 1, 2, or 3? 2 would be, how did you get that? You took the negative log of each of them. So to prove your work, I'd want you to take the negative log of each of these. And when you do, you get 6.38, you get 7.21, and you get 1.89. Obviously, that's closest to what we're looking for, okay? So that being said, A says, from the systems above, identify the conjugate pair that is best for preparing a buffer of pH 7.2. So the best pair would be H2PO4 negative and HPO4 negative 2, because the pKa is equal to 7.2. That's all you need to say. Yeah, they're trying to simplify it. That's going to be the simplest way. And even if the two concentrations aren't exactly the same, they'll be close enough that it'll still be your best option. All right, part B. Explain briefly how you would prepare the buffer described in A, which is buffer number 2, with the conjugate pair chosen. This is just semantics. I want you to get used to this. I'm just basically going to tell you what you need to write. You're going to need to say you would mix. Oh, great. It always acts up this time of day. Mix equal. Oh, my gosh. Looks like I'm just like, what is going on? Here we go. Mix equal concentrations and volumes of, oh, this is frustrating me. Mix equal concentrations and volumes of the salts containing those ions. They need to be salts containing those, because I can't go to the chemistry store and buy a bottle of this. I can buy NaH2PO4 or NaHPO4 minus 2. I mean, not minus 2, or Na2HPO4. I can't buy the ions alone. So equal volumes and concentrations of the salts containing the ions above. Okay? So that's basically what you need to do to make that pH, because making them equal in concentration and volume cancels out that ratio in Henderson-Hasselbalch. All right, that was B. C. I think I've asked this question 87 times now. If the concentration of both the acid and the conjugate base was doubled, how would the pH be affected? Not, because the ratio doesn't change. All right. This one is super sexy. I'm a big fan of D, not just because it's my initials. Explain briefly how you would prepare the buffer solution in A, meaning this one. How would you make this if all you had was one of those salts and a strong acid or base? So which one do you can pick either one. Which do you want, the left salt or the right salt? Okay, we're going to say we have the left salt, H2PO4 minus. If we wanted to make the buffer, we need to create the conjugate. So what would we mix with that to make the conjugate? A strong acid or a strong base? a strong base. If we make the add it to it a strong base, we're going to get HPO4 minus 2 plus water, which is perfect. So you would say you'd mix the strong base with, just pick sodium, don't worry. Mix strong base with sodium dihydrogen phosphate, NaH2PO4 to form the buffer. So you understand now, if I had chosen, we had chosen the salt on the right, what would we have mixed it with? A strong acid, right. Had we chosen that one, we would have had to have add H plus to it. Okay, I really like this. This is really showing you kind of understand how these conjugates work. Okay. Oh, I get to answer the phone. How exciting. All right, last problem. Again, I'm going to try to make this a little bit smaller so I have some more room. Again, those of you at home should have your own paper so you can write. All right, this is the problem where if you can do this from beginning to end, you're golden. Obviously, when I'm doing it with you, it's going to be easy, but this is the level of problem that you're going to see on the AP, okay? So in water, hydrozoic acid is a weak acid. Be careful. A lot of students do this and they write NH3 instead of HN3 because you're used to writing NH3. Just be careful. This is a weak acid and it gives you the Ka. Part A says, write the expression for the equilibrium constant for Ka. Well, we need Ka, but we usually need a reaction to see that, right? So it's a weak acid. How do we write a reaction for that? Add water to it. So that's HN3 plus water. And what do we get? H3O plus and N3 minus. All right, so now we can write our expression. So it's N3 minus times H plus or H3O plus divided by HN3 concentration. All right, there's our Ka. Part B, calculate the pH. And this is how the problems usually work. They start out simple, still pretty simple, and then all of a sudden, bam, it hits you over the head, and you're like, what is going on? Part B then says calculate the pH. So how do we find the pH of a weak acid? Of a weak acid, not negative log, Rice table. So we have an original concentration. Our acid is 0.05 molar. Don't worry about that liter. They're just telling you how much you have. I don't care if you have a swimming pool of this stuff. If it's 0.05 molar, the pH is going to be the same no matter how much you have. So we have an original concentration of 0.05. 0, 0, minus X, plus X. Plus X, 0.05 minus X, X, and X, negligible. Okay, so we're going to plug into our expression and we get X squared over 0.05 is equal to the Ka of, looking above, 2.8 times 10 to the negative fifth. So when we do that, we get X, and again, this is the mandatory step. X is equal to the concentration of your H+. You have to indicate that, and the other class got X to be, they didn't give me X. Give me X. 1.2 E negative 3. And then that ended up giving us a pH of 2.93. Y'all get that pH? 2.93. Bam. Part B is done. Part C, pH of a solution is needed. We have 0.150 liters of this solution. And the big picture here is we originally started out with 0.3. And what they're saying is, okay, we're going to use half of it for this part and the other half for that part. So that's the only why they're giving you that. You will need that to find moles. So I just want you to make sure that you see you're just splitting that solution in half. So what is that solution again? It is a weak acid solution. To that weak acid in part C, what are we doing? Are we invading? What are we doing? No, what are we doing? We're just taking the HN3 and we're adding NaN3. What are we creating when we do that? N3 minus is in there, so what did we just make? Remember, that's N3 minus. What is this? That's a buffer. You see that? Do y'all see we're making a buffer? Okay, so we're putting 0.8 grams of sodium azide into the 0.150 liters of water. So we need to know how much sodium azide is going in there by finding its molarity. So in order to get the molarity, I need to just treat the sodium azide as it's a salt together. So we have 0.8 grams of that divided by the molar mass is 65.02, and that comes out to be 0.0123 moles. But to use Henderson-Hasselbalch, I need molarity. So I'm putting that solid into how much solution? 0.150 liters. So that's going to give me a molarity of sodium azide of, I can't find it, 0.08? 0.08, is that what y'all got? Okay, so that's equal to the N3 minus concentration. What was the concentration of the acid? They gave it to us. Where did they give it to us? Right there. So that's equal to 0.05. So how do I find the pH? Henderson-Hasselbalch. pH is equal to negative log of 2.8 times 10 to the negative fifth plus the log, what's the ion concentration? Which one? 0.08 over 0.05. So you should have gotten a pH. They got 4.76. Yeah? You see how this could get confusing? This is where you know how to do all the individual things, but you get lost as to where stuff's coming from. And this last one, this last part just irritates me because it's just ugly. But it's definitely nothing that you can't do. So let's tackle it and we'll be done. No questions on the one we just did? All right. To the remaining one, now we're doing something else to the other half. We're adding 0.075 liter of 0.1 molar OH minus. So what kind of problem is this? Invasion. We're adding OH minus to the other half of the HN3 solution. And what is that going to give us? N3 minus and water. So we need moles of each. To find moles of our OH minus, it is 0.075 times 0.1, right? So that's 0.0075. For HN3, we're taking 0.05 molar times 0.150, which is 0.0075. And then we don't have any of that yet because it's not a buffer yet. We're going to lose 0.0075, lose 0.0075, gain 0.0075 moles. What does that give us? 0, 0, uh-oh. We haven't seen this scenario since early on Friday. What kind of situation is this? No. Yep, it's a hydrolysis situation. So what do we have to do this now? Add water, but there's still something more important. Yes, convert to molarity, because we have moles here divided by a total volume. It's 0.150 plus 0.075 comes out to be 0.225 liters, giving me a concentration of 0.033 moles per liter. So now I start a flipping rice table. This is why I don't like this problem so long. and I'm going to have to write like microscopic to fit it on the screen. We get, and I'm going to rush through this because of the bell it's about to hit, plus water gives us HN3 plus OH minus. Original concentration we get from what we just calculated, 0.033, 0, minus X plus X. There's one more issue. What is the last issue when we do hydrolysis? Yep. Oh, I have no room. I'm going to write way up top here. I'm going to erase this. I can, but I have to get out of, I can't do it from the screen. I have to minimize it and then extend it, and I'm not going to do that. So now I'm going to set this up where I'm going to have 1 times 10 to the negative 14th divided by that Ka they gave us of 2.8 times 10 to the negative 5th is equal to the x squared. I can drop that 0.033 minus x because it's negligible. I end up getting an x which is equal to the OH concentration, which is all I need to solve. 3.4 times 10 to the negative 6 moles per liter. Yep. This is why these problems are crazy confusing. All right. We start titrations tomorrow.